Hello, everybody, and welcome back to Math 100. So today we are going to start Chapter 6. Chapter 6 has two big concepts. One is the exponential, the idea of exponential growth, and the other is the opposite, which is called logarithms. Okay, behind me in this background, you see the number E, which is a sculpture inspired by this mathematical concept of the irrational number E. Now you've seen this before because this showed up in the continuous compounding back in chapter 3. But it is a very important number, as I mentioned before, and this plays a central role in the study of calculus and other sciences as well. So this is, by the way, and on the campus of MIT, the Massachusetts Institute of Technology in Boston, or in Cambridge, Massachusetts. All right, so we will start. We are not going to use this particular number, but we are going to dive into the world of exponential growth in section 6.1. Let's get started. All right, the topic for section 6.1 is linear versus exponential growth. We had a very similar discussion when we began talking about simple and compound interest. And in fact, simple is linear and compound is exponential growth. Here's the main question. What's the difference between linear, not surprisingly, and exponential growth? Okay. And so you will see that there's a world of difference, and that is a key role, idea of this section. So there are two basic types of growth, and obviously you know what they are. One is linear, and the other is exponential. First, linear growth. What is linear growth? It is growth by a fixed quantity. Now, you remember back in compound interest and simple interest. Remember, simple interest grows or is added onto the account, and it's always the fixed number of dollars, fixed quantity. All right. So this is the key idea, fixed quantity. All right. As opposed to later we'll see a fixed, well, blank. Okay. So that is not quantity here, but anytime you have linear growth, we call the growth a fixed quantity growth. All right. And so an idea is, it's an example is simple interest. And there is a common difference between the two consecutive terms of such growth. All right. And so let me contrast that with the exponential growth. In exponential growth, we talk about a fixed what. We talked about this again in the context of finance, growth by a fixed percentage. Okay, when the population or a number or frequency or whatever grows by a fixed percentage, it grows exponentially. Exponential growth. All right, and so an example is compound interest, and then in any of these, there is a common percentage increase, which we call that the growth ratio or the growth rate. And so there is a common ratio, which we often symbolize or denote with the lowercase letter r. Right? What's written here is pretty important as well. This happens whenever the rate of growth is proportional to the present quantity of population. It may be difficult to understand this, but in the world of science, biology in particular, many things like the number of bacteria or the number of species of a certain animal grows at the rate which is proportional, directly proportional to the current quantity, current population. So as the population grows, the rate of growth itself gets faster. Okay, so in terms of visual understanding, of which I think is pretty important, right? So let me just draw a little quick picture of what the continuous growth is. I mean, what the linear growth is, and what the exponential growth it looks like. All right, so in linear growth, you start at certain number. Okay, let me go ahead and write down some ideas here. This is time. As time goes this way, the quantity Q goes that way. Okay, so the vertical axis represents a quantity and the horizontal axis represents time. And so in linear growth, you start with some point and the growth is basically on a straight line. And there's a reason for it. And the reason is precisely because the growth rate is by the fixed quantity. All right. So let's say you start, and by the way, this point, sometimes called the y-intercept in your algebra class, more applicably, we will call that the initial value. See, because it's called the initial value because when t is 0, that's the initial condition, initial point. This is a quantity at the beginning. And then let's say every time increases by 1. Let's say this is in a number of years or something, right? Maybe the increases by, let's say 100. Okay, so every year it increases by 100. So you have another year, goes up by 100, another year, it goes up by 100, another year, goes up by 100. And if you plot all of these points, the curve basically becomes a line, a simple straight line. And that's why it's called linear growth. Okay, the word line is right here, right? Exponential is different. Let's say you start at this same point, the initial point or initial quantity. It grows by, let's say, 5% here, right? And then another 5%. But remember, this time the 5% is based on the new current balance or current number. And so this is a terrible picture I'm drawing here. All right, so if you do this right, the exponential growth can be described in this way. It just kind of grows this, in a very curvy way. And this curve has a characteristic. It is always increasing. And the rate at which this number is growing is also increasing. Okay, so not only is it increasing, it increases faster than any straight line like this. All right, so that is the difference between these. All right, so whenever the rate of growth is fixed, okay, then we will see that the growth is exponential. All right, let's go to the examples that I have here. Town L, surprisingly, stands for linear, E stands for exponential. Let's assume we have 2 towns, okay, and they have the population of 10,000 at the moment. The growth of town L, the linear town, is by 500 a year. Okay, now we are going to learn how to express this kind of growth and then the exponential growth in 2 types of formulas. The first one is recursive, and like the word says, it's recursive. All right, so it represents what happens next. So P naught, by the way, whenever you have 0 as a subscript in mathematics, we read this as naught. Okay, so this we pronounce as P naught, and this is the correct proper spelling. Okay, and so that's how you read this. P naught is the initial value or the initial quantity. This says the initial quantity is 10,000 because that's a current population. All right, and then it grows by 500. So what we write in under the recursive formula is this: P sub n, this is the population in years from now, is what do you do with the previous number? So the previous number, whatever this is the previous year's population, and you add 500 to it, right? So this is the formula. You add 500 to the previous number. This is the population of the year n-1, and you add 500 to get the population of this town in year n. So together, these 2 equations are called the recursive formula for describing this kind of linear growth. Get that? Okay, make sure you write this down because you will have questions in your homework where you are to write recursive formulas. The explicit formula is more general. See, the problem with this recursive formula, I mean, it's easy to write, but the downside is if I were to ask you what the population of this town L is 20 years from now, you have to go back and you have to know what the P19 is. And to know what P19 is, you have to know what P18 is. And so that's nice in the sense that we build on the previous year, but it's not very convenient. All right, so for that we have explicit or something more explicit. It's called the explicit or general formula. Now notice here, every year you're adding 500, right? So you start at 10,000 and every year you add 500. So after n years, of course, all you have to do is to add n times 500. And so that would be called the explicit formula. And there's only one explicit formula. For the recursive, you have to have two. Okay. So linear growth can always be written this way, right? Maybe I should also mention here in different color. This is the initial. Whatever you see as a constant is the initial quantity or initial population. We call that the y-intercept in algebra. Okay, you don't have to call that. That's just purely from the algebraic standpoint or analytic standpoint. This number, well, not this, 500 is the number of increase every year, and so that is the slope. Okay, and that's the, again, algebraic language. We can call that the rate of growth or the quantity of growth. And then of course n is the variable, you know, and that is the number of years since the beginning. Okay, so that is town L, the linear town. The E, the town, the exponential town. This is where the population grows exponentially, and this is more natural. For instance, if you look at the population of the world, it roughly grows exponentially. All right, so it grows by 5% a year. All right, in the recursive formula, again, we start with the initial quantity, and then we write what Pn is based on P sub n minus 1. Now, what do you have to do to the previous year's population to add 5% to it? Well, that's pretty simple. You just multiply this by 1.05. Remember, many times we write the constant first. It's 1.05 times P sub n minus 1. And because multiplying by 1.05 results in the total after adding 5%. Now we saw this in chapter 2 and chapter 3, so this should be pretty simple. These two formulas or two equations together constitutes the recursive formula. The explicit formula is very similar to what we saw for the general formula in compound interest calculation. How do you find P sub n? Well, it is 10,000, the initial account back in chapter 3, multiplied by 1.05 raised to the nth power, right? Remember that? Because, you know, first year you multiply by 1.05, then the second year you multiply the result of that calculation by another 1.05, and then the following year by another 1.05. So the number of times you multiply 10,000 by 1.05 is going to be that number n. Make sure you do this part first on your calculator, okay? Because otherwise, I mean, if you take 10,000 times 1.05, and then if you raise that to the nth power, you get a number that's way too big. It may be difficult to see these two lines here, but this is the linear growth curve, and this is the exponential growth curve. At the beginning, there isn't much of a difference. Okay, if you look at around here, the difference is very little. But if you give enough time, the number of the population difference is going to be enormous, right? And that's the difference between exponential and linear growth. Now, in everyday English, you know, you hear people talking about things like something's growing exponentially, right? The number of, let's say, Instagram users is growing exponentially. That's what this means. Okay, what they mean by that is it's growing faster and faster, because even though it's based on the same percentage, if you look at the sheer numbers, okay, they grow much faster as time continues, and that time goes on, and that is called exponential. All right, so let's take a look at these three quick examples. By looking at the formulas, I want you to tell me what kind of equations we are having, what kind of growth, and what is the rate. What can you understand from the equations? Okay, you may want to pause this and then answer these three questions and come back when you get the answer. In fact, this may be a good time to stop part 1 of this section. And so when you come back, once you think you are done with these questions, you can start on part 2 of this section, 6.1.